Okay, so the geometry, the formulas will be given to you, but all the math you still have to do with your brains. So related rates, the water runs out of a conical tank. That means a tank in the shape of a cone. Okay, so let's see, the radius of the top, I'm assuming then the tank is shaped like this. Would you assume the tank is shaped like this? With its vertex down, I mean, it's not a very efficient way to make a tank, but it works for the math, right? It's a very, very neat geometric way to do a tank. So we have a cone with its vertex down. The radius of the top of the tank is 5 feet, and the height of the tank is 10. So that's important to know. So we have a 5-foot radius and a 10-foot deep or a 10-foot tall tank. And water is running out. So let's go ahead and we'll put a spout and the water's running out down here, making a nice puddle on the ground. There we go. Water's running out. We know the rate. So if water is running out, what is changing? The volume. The volume is what's changing. We are given volume. Water is leaving the tank, so the volume of water, the amount of water in the tank is decreasing. Okay, that's number one, identifying what we're even talking about. So decreasing, so I'm gonna make this a negative 2 cubic feet per minute. So that's our rate at which the volume is changing. It is losing water, which is why we have a negative 2. Okay, so all the things should be getting smaller. The radius should be getting smaller. The height should be getting smaller, right? All of our answers should be negative when we're looking at what our answers are going to be. Okay, how fast is the water level shrinking? Sinking, shrinking? Sinking. How fast is the water level sinking when the water is 4 feet deep? So does that mean the radius or the height? That's the height, right? We know that the height of the water, so maybe it's here. Maybe this is going to be our 4 foot deep water level. I should have changed colors and made this blue. Okay, so there's our 4 foot deep. What is the dH/dt, the derivative of the rate of the height of the water? Right, that's what we're talking about. The height of the water is getting smaller. What is the rate getting smaller at? Okay, so that's what we're being asked. We know the volume, the way the volume is changing. We're being asked to find something about the height. Okay, so there's one dimension that we don't know anything about. And what dimension is that? The radius. We don't know anything about the radius, right? We're not asked about the radius or its rate, which means the radius might not be important to our problem if we don't know any information about it. So let's go back and start with our volume, right? That's something that we knew though. Volume of a cone is that formula up here? Volume, 1/3 pi r squared h. So we'll start with the volume 1/3 pi r squared h. Now here's the problem. There are 2 variables, right? We're only asked about one variable, the height. So can we express this formula in terms of its height? Right? That's our first job, is to write our formula without an r in our equation. We want to somehow replace our r. So here's what your brain needs to think. Is there a relationship between r and h? So let's come over here and see if we can explain this. If I compare the radius to the height, what is the ratio of the radius to the height? 1/2, right? Which means if the height is going to be 5, that means the radius is going to be 2.5, right? Because it has to change in proportion. As the height gets smaller, the radius has to get smaller. And it changes at a proportion because we have a nice right triangle in there. So we can create this proportion of radius compared to height. Okay? So radius over h. Anytime we have a cone problem, this is what we're going to want to do. And they don't tell you to do this. You have to know this on your own. It says the maximum radius is 5 when the maximum height is 10. Okay? The radius over the height, that ratio, the comparison. And we can compare them because this is a right triangle. And every time we make another height, it's now a similar right triangle. And similar triangles always have a proportion associated with them. So coming back over here, I want to replace r in my formula, which means I need to solve for r in my proportion. Okay, I want to replace r in my formula, so I have to solve for r in my proportion. So I multiply both sides by h, and what does r equal? Basically h divided by 2, right? The radius is always going to be half of the height. Okay, now that's not even part of our problem, right? That's only going to go in here so we can simplify our equation. We're going to replace r with h over 2. Okay, this is the first of our hard steps. Anytime we have a cone problem, these are the steps that we need to do. Okay, so first we find the ratio between the radius and the height. And now we have to simplify our equation. So let's do our squaring. We're going to square h and we're going to square 2. Square h and square 2. So that means I have 1/3 of pi times h squared over 4. And I'm still multiplying that by h. Okay? So we haven't done any calculus yet. This is all algebraic simplification and geometry. So now let's multiply all of our numerators together. We have a 1 times a pi times an h squared times an h. That looks like it's pi times h to the 3rd power. And then I multiply my denominators together, so I have 3 in the denominator and I have 4 in the denominator. It means I have a denominator of 12. So here is my volume formula. The volume of my cone, in terms of its height alone, is pi times h cubed divided by 12. Okay, and maybe for funsies, we want to write this as pi over 12 times h cubed. Right? Because pi over 12, that's a constant. That's a number. H cubed is my variable. Because now I want to perform the calculus and take its derivative. So we start with v. The derivative of volume with respect to time, well, that's dv dt. Equals, right? So now I'm looking at this formula right here, pi over 12 times h cubed. So I'm going to leave my constant alone. Pi over 12 is my constant, so it stays there. And what's the derivative of h cubed? 3h squared. And I also have to take the derivative with respect to time, which would be my dh dt. Every variable in our equation gets derived with respect to time. So we have our pi over 12, we have our 3h squared, and we have our dh dt. Okay, now let's go. dv dt, that was -2, right? That's the volume of water, the rate at which the water is running out of our cone. We have pi over 12, that's fine. We want to know when the height is 4 feet. So you plug your 4 in for h. And our solving for is our dh dt. So that's going to be our last part of our formula, dh dt. Okay? And that's what we want to solve for. So eventually we're going to end up dividing by all of this stuff. So let's see what this stuff is. 4 squared, 16. 16 times 3 is 48. So there's 48 pi over 12. 48 divided by 12 is 4 pi, right? And we still have our dh dt equals -2. So our last step is divide by 4 pi. And let's reduce this equation. So 2 over 4, that reduces to 1/2. So dh dt is -1 over 2 pi. It's the height, so our units are feet per minute, right? And it makes sense that it's negative because our height is getting smaller. The depth of the water is getting shorter and shorter, so we have a negative rate of height changing. Just makes our answer look good, right? It's changing at a rate of losing 1 over 2 pi feet per minute. Okay, next, the classic man walking underneath a light pole problem. Okay, so I know it's hard to read, but this man is 6 feet tall, and he's walking at a rate of 5 feet per second toward a flagpole, towards the flagpole. So his movement is going this direction. Okay, so we'll figure out what variable we want to call that in a minute, but it might be x since that's the horizontal motion. Okay, so if we're going to call this x, then there we go. So dx dt is 5 feet per second. Makes sense. And the light pole is 16 feet. So some things that don't change. The light pole's height never changes. The man's height never changes. He doesn't get shorter as he walks towards the light pole. It's the same height the whole time. At what rate is the tip of his shadow moving? So that's this point right here. When he is 10 feet from the base of the light pole. So when this is 10, what is dx dt? Well, we'll figure it out. So this is the shadow right here. All right, so we'll call this S. No, I don't want to call it S. S and 5 look a whole lot alike. Let's call it, I don't know, make up a letter. W's don't look like 5s, but my S's do. So I try to never have the variable S in any equation ever. Okay, so what type of a problem is this? Right, so let's draw this triangle. Both of these people, we're assuming that this man is walking perpendicular to the ground. Right? He's not a hunchbacker walking over. We're assuming that the pole is also perpendicular to the ground. So what we have here, in fact, is a set of similar right triangles. Okay, this is a similarity problem, not a Pythagorean theorem problem, right? Because we don't know anything about the length of the light, right? This is the light that's hitting the man's head so that the shadow is falling behind him as he walks towards the light. So this is a similar triangle, aka proportion. So let's write our proportion. Looking at the big triangle, what is the height of our pole? That's 16 over what is the base of my triangle? 10 plus W, right? The whole entire length from the flagpole to the tip of the shadow is 10 plus W. At the same time, let's look at our triangle created by the man, who happens to be 6 feet tall, and the base of his triangle is just W. Okay, so anytime we have a guy walking towards a light pole or away, this is a proportion problem, not a Pythagorean theorem or any other type. It's a proportion. So first of all, let's solve this for W. Okay, let's solve it for W. We first do that by cross multiplying. Cross multiply. 16W equals 60 plus 6W. All right, I have to multiply it by the 10 and the W. I need to distribute. So solving for W means I bring my W over here, right? That's now 10W equals 60. So that means W equals 6. Oh, so the man has a shadow of 6 feet long when he is 10 feet away from the light pole, which doesn't seem right, right? We haven't done anything to take a derivative yet. We need some more variables. Okay, let's go back up and change. Oh, at the moment, we don't know this is 10, do we? We know that that's something, but it's not 10. At the moment it's 10, his shadow is 6, right? This is the shadow. But not when we make our formula. There we go. That's what we're missing. So we're going to replace our 10 with a D. We can do this. Don't worry. We can do this. This is D. So not a whole lot changes. We still have 16W equals 6D plus 6W. So 10W equals 6D. And what do we want to solve for W? Let's solve for W. So we'll divide both sides by 10, and we'll get W equals 3/5 of D. The shadow is 3/5 of the distance the man is away from the pole. Okay, we'll say that's okay. So now we have to take a derivative, right? We want to find the rate of change of W, right? The rate at which the shadow is changing. What is the rate of the shadow changing? Okay, so now we can do this. What's W prime? dW dt equals 3/5 of d dt. I guess it wasn't a very good idea to use d as my variable, huh? Right, so your variable is here, the derivative of distance with respect to time. And our problem said this was 5 feet per second. So we're going to plug in 5. I called it dx dt up there, but I guess this is dd, the distance you are away from their pole. So 3/5 times 5 is 3 feet per second. So when he's 10 feet away, the shadow is changing at a rate of 3 feet per second. Part B, what is the rate, at what rate is the length of his shadow moving? When he is 10 feet away from the base, the length of his shadow. So that was the tip of his shadow. Maybe we just figured out part B, and we need to go back and figure out what part A is, right? Because part A, the tip of his shadow, I don't know, is way over there. Let's think about this for a second. We're going to use another set of similar triangles. Okay, so we have, so basically we're looking at the tip of the shadow, this whole entire distance here, right? That whole distance is representing the tip of his shadow. So let's call that y, just to throw in another letter here, just for fun. So if we do it, it's going to be 16 over y, right? It's the proportion, the pole over the entire distance equals 6 over w. Okay? So we can cross multiply here and we get 6y equals 16w. Now, so let's go ahead and let's take the derivative of this, right? Before we saw, actually, sure, let's solve this for y. So y equals, divide both sides by 6. We can reduce this to 8 over 3w. Okay, so now let's take the derivative with respect to time. So we're going to have a dy dt, and that is, right, remember, y is the entire length all the way out to the tip of his shadow. So that's what we want to solve for, equals 8/3 of dw dt, right? Well, we just figured out dw dt, right? The rate at which the shadow is changing was 3. So this is really 8/3 times 3. So if we multiply these, we cancel out the 3's and we get 8. So his shadow is changing at 8 feet per second. Now, thinking about the direction, right, if we consider the positive direction moving away to the right and the negative moving towards, both of these would be negative because you're moving towards, I guess, towards the pole, right? The left direction is the negative, quote-unquote negative direction. So the first thing we did was we found B, the rate at which the length of the shadow, so W represents the length of the shadow. We first found part B, and then we needed that to figure out what part A was, because we have our dW dt in there. Okay, so some wonderful related rates problems. Have a great day.